At the poles, the sun strikes at an oblique angle, and what little light there is gets reflected back out to space by the ice and clouds. These are the primary reasons why the poles remain cool. At the equator, it's a very different story. Not only does the planet receive more direct sunlight here, the lack of ice means that less of the sun's energy is reflected back into space. And at the equator, the sun's concentrated energy fuels a heat engine that can trigger weather events around the world. Perhaps the best place to see the impact of the sun's heat is an area in the Atlantic just north of the equator and west of Africa, the coastal waters of the Cape Verde Islands. Here, the sea provides a living. The local fishermen keep a careful eye on the weather. They know that storms can bring a good catch. Turbulent weather stirs up nutrients from the deep, attracting great shoals of fish. It's the hottest time of the year, and the sun beats down relentlessly. By late afternoon, the huge inflow of heat energy has led to the buildup of large cloud formations. Sometimes these formations develop into massive storms. It's a process that satellites are revealing in fine detail. Circling above the fishermen is a NASA satellite called Aqua, Latin for water. It orbits the poles. One of its key tasks is to monitor the complex interaction between sunlight and water.
Aqua satellite is one of NASA's flagship satellites. Its primary function is to study the hydrologic cycle on Earth. Vapor in the atmosphere, liquid ocean, the temperature of that ocean, and the ice.
One of Aqua's instruments looks down at the sea around Cape Verde, again in infrared, sensing heat. Highlighted here in yellow, over 1 million square miles of ocean reaches a critical temperature, 80 degrees. At this temperature, the sea is evaporating fast, producing an invisible gas, water vapor.
By looking at the infrared, the Aqua satellite is able to measure the amount of water vapor evaporating from the surface of the ocean.
Aqua shows that this area is producing millions of tons of water vapor every hour. Based on that data, it's possible to create an image of what the vapor might look like if these fishermen could actually see it in the air around them. Water vapor is much lighter than air, and vast columns rise upward directly from the surface of the sea. The water vapor carries with it heat, the energy of the sun.
Well, water vapor is like invisible energy. It's like molecules escaping the ocean, taking heat energy with them. And they're like little mobile solar collectors that are zipping around the atmosphere.
Half a mile up, as the air cools, the water vapor condenses back into liquid water, tiny droplets that form vast clouds. The vapor releases the sun's energy, the heat it received earlier. The result is a storm.
Molecules condense in the atmosphere and become liquid again. And when that happens, that heat is given off into the atmosphere, and it warms the atmosphere, and that's the heat that powers storm systems.
In the worst storms, The heat captured by the water vapor is equivalent to up to 200 times the global production of electricity at any given moment. The process of evaporation results in something we don't need special instruments to see. The rising heat drives the clouds up to 10 miles high. As the clouds rise upward, the Earth's rotation causes them to spin. The thunderclouds merge into a vast vortex. This is the birth of a hurricane. It is 2005, the busiest hurricane season on record. On August 27th, a meteorological satellite is tracking a Category 3 hurricane that started in the Bahamas. Its name is Hurricane Katrina. Throughout the region, there is one question on everyone's mind. Will the hurricane hit land, or will it blow itself out? The answer may come from a NASA satellite called TRMM, the Tropical Rainfall Measuring Mission. TRMM is equipped with a radar and imager that operate in the microwave range of the spectrum. These are higher in energy and shorter in wavelength than other radio waves. The instruments bounce microwaves off raindrops in the clouds, allowing scientists to build a three-dimensional model of the internal structure of a hurricane.
We can actually look at microwave energy, which is generated within the clouds and coming from the ocean surface. It's almost as if the clouds are now invisible to us. We can see right through them, like taking a CAT scan to look inside those clouds.
This satellite is a powerful tool, and now its sensors reveal something ominous. Huge vertical columns of warm water vapor burst up from near the center of the storm. Almost like hurricanes within hurricanes, these climbing vortices deliver added infusions of energy into the heart of the storm, fueling its growth even more. These new sources of energy are called hot towers.
If they occur in the right place at the right time, near the very center of the system, they could be like a giant spark plug that gets that whole engine running at very, very high speed.
The hot towers draw more and more water vapor off the ocean. This triggers a feedback loop that leads to a runaway reaction. In just 24 hours, Hurricane Katrina grows into a Category 5 monster. All this violence is a direct result of the power of the sun on the ocean. Ferocious winds blow for 2 days straight, reaching 175 miles an hour, twisting steel like paper and ripping apart homes and buildings. Over 3 trillion gallons of rain a day and a massive tidal surge from the Gulf of Mexico combine to inundate whole areas of the Gulf Coast. Katrina leaves its mark across 90,000 square miles. Over 1 million people are displaced. Katrina becomes the standard by which future hurricanes will be assessed. But even this extreme hurricane is just a tiny brushstroke in a much bigger picture. A picture of how the sun drives water around the entire planet, with radically different effects in different places, all under the watchful gaze of our eyes in space. Take just a single day in July. In New York, commuters swelter in 95-degree heat. Searing winds pump hot air into the region from the south, creating oppressive, humid conditions. 7,000 miles away, in Mumbai, India, commuters here struggle to cope with torrential rain. The deluge comes so fast that the streets are flooded in hours. Meanwhile, in Chile, the desert of the Atacama is almost totally dry. There are places here where rainfall has never been recorded. Such diverse environments, thousands of miles apart, appear totally unrelated. But by pulling back for a wider view, we can see that they are, in fact, intimately connected. Orbiting 22,000 miles from Earth's surface is a chain of 5 weather-tracking spacecraft, including this one, GOES East, operated by the National Oceanic and Atmospheric Administration. GOES is an acronym for Geostationary Operational Environmental Satellite. Each moves in a fixed position relative to the Earth, called a geostationary orbit. They always look down on the same parts of the planet. The combined data from these 5 satellites give scientists a unique perspective on the Earth.
By having several of them located at different positions around the equator, we're able to get a view of the whole Earth 24 hours a day.
By observing the entire Earth, these satellites reveal how energy moves throughout the globe, beginning with the impact of the sun on water. The process is the same everywhere, but the outcome will be very different in different places. Converted from the numerical data, these 5 circles graphically depict what the satellites actually sense. They reveal the total picture of water vapor produced on Earth in a single frame. Seen here in fast forward, 1 second is equal to a day. It shows how water vapor produced at the equator continuously transports the sun's energy towards the poles. Local landscapes and topography affect the vapor's impact, with results unique to each region. In India, at the end of July, the warm water vapor is drawn from over the ocean by the difference in temperature between land and sea. Rising to high altitude, the vapor cools over the land and condenses back into water. We call the result the Asian monsoon. Nearly 1 trillion tons of rain falls out of the sky, transforming parched land into fertile plains. The monsoon eventually moves to the east, reaching China, where it floods the paddies that are ideal for growing rice. This process helps provide food for 3 billion people, almost half the world's population.